Good day, Matrix, and welcome back to our Learn Extra Geography sessions. Today we will be looking at part 3 of geomorphology, which focuses in on our structural landforms, which is a relatively simple section of the geomorphology work. We will be going through a bit of a theory work and what's important to understand and highlight the most important concepts, and following after that we will be doing a whole set of questions and answers and how you should attempt to be answering these questions for the final exam. So let's look, and we're going to be starting, as I said, with our structural landforms. And very importantly, if we look at the 3 key types of structural landforms that we will be looking at in grade 12, we will look at the topography of a horizontal strata, so that is strata that lies horizontally in terms of the Earth's surface. We will look at landforms that are associated with inclined rock structure or strata. Inclined rock strata, grade 12, just means that the strata is sitting at an angle to the Earth's surface. And lastly, we will look at landforms that are associated with igneous intrusions. So those are the 3 main sections that we will now look at individually and understand what needs to be learned for those 3 separate concepts. So just a reminder, we're going to look at horizontal strata, inclined igneous rock strata, and obviously igneous intrusions. So our first type of strata, as mentioned earlier, would be our horizontal strata. And like I've mentioned before, horizontal means that it is lying in almost parallel layers to the Earth's crust. According to the notes that we can read, it says sedimentary rock with igneous sills that are horizontal to the Earth's surface. The fact is that they are lying flat and parallel, therefore we give them the name horizontal. Second point mentions that we have harder sills as part of our horizontal landscapes, which prevent erosion and form flat tops of these landscapes, and the example that they give you is the plateau of Lesotho. Now, very importantly, we learn these concepts because in geography our most important horizontal landscape that we look at is a Karoo landscape, which is predominantly found in the Northern Cape. The third point then goes on to mention that plateaus, which is how the horizontal strata originally begins, are cut smaller into mesas, buttes, and when the hard rock layers are removed completely, these layers form what we call conical hills. Just a reminder that in between a butte and a conical hill, we can also get what's referred to as a pointed butte. It is just a smaller version after a butte has been eroded even further. Okay, in dry areas, and that's very important, these Karoo landscapes form where the conditions are arid, almost desert-like, very little rain, very little vegetation, where exotic rivers, please remember that term. That term comes from your fluvial geomorphology, and an exotic river, grade 12s, is a river that will start in a high rainfall region, so getting a majority of the rain, more than like 800 millimeters per annum, and flow through an exceptionally dry region in a particular country. The example in South Africa of an exotic river is the most important river in South Africa being the Orange River. The Orange River has its source in the mountains of Lesotho, which is an exceptionally high rainfall area, and it flows westwards towards the Atlantic Ocean, and it flows through South Africa's Northern Cape province, which by now you should know is a very, very dry desert-like province. It then says canyons develop due to the dominance of stream erosion and the absence of sheet erosion. Stream erosion versus sheet erosion. Stream erosion happens where the water is flowing within the river channel and carving its way through the landscape, as opposed to sheet erosion where the water flows in sheet-like layers across the Earth's surface. So stream erosion refers to the water eroding the landscape within particular channels, and sheet erosion is where the water is not moving in a specified channel but rather moving in its layers across the Earth's surface. In areas with uniform rocks means that they have a similar hardness, okay, and that's in terms of the erosion rates of these rock strata. Okay, so if we speak about uniformly resistant to erosion, they are equally erodible in all parts. Hilly landscapes will develop like the Badlands in North America. We also have an example of hilly landscapes in South Africa, and that would be in the KwaZulu-Natal region. So hilly landscapes are also found here in South Africa. Okay. Like I said before, the most important topography of horizontal strata that we look at is what we refer to grade 12s as the Karoo landscape. Like I mentioned earlier, that Karoo landscape is found within the Northern Cape province. All right, and the features associated with that Karoo landscape are things like our plateaus, our mesas, our buttes, our pointed buttes, and our conical hills, which you need to learn and to remember these terms. It says a plateau is cut down into a mesa. Mesas are then further cut into buttes, and buttes become conical hills. The plateau then is changed into a plain surface. If we can look at the two diagrams in front of us here, we will see that these structures here are the horizontal layers that form a Karoo landscape. And what happens is over time, a river flows on the top of that landscape, and because rivers erode vertically downwards, it starts carving channels between that plateau. You will then see that we get a plateau which is a much larger area of horizontal landscape, and over time it gets eroded according to its parallel sides, and therefore it shrinks and becomes smaller, and therefore we get a mesa. After a mesa, you will see in the next diagram, a mesa is further eroded down and we create what's called a butte. Okay, obviously a smaller version of that butte would be what's referred to as the pointed butte, and as soon as you will notice that all of these features, the plateau, the mesa, the butte, if we were to color in this area over here, that area represents what's called the hard rock top of the particular landscape. And if you look, the butte has one, and the last feature of our horizontal landscape is what we refer to as a conical hill. And if you notice in the diagram, the major difference between the conical hill and all the other features is once the hard rock layer has been removed, it then becomes known as a conical hill. So very important, you must remember that for a horizontal landscape, you dominantly look at what's called a Karoo landscape that's found in the Northern Cape, and furthermore you should remember that all the different features that are associated with that landscape, for example the plateau, the mesa, the butte, the pointed butte, and the conical hill. Alright, moving on, we're going to look at landforms that are associated with inclined rock strata. That specific word inclined gives you an idea of what kind of rock strata we're looking at. The word inclined actually means rocks that are lying at an angle. So some of the force has been at play that has caused the rocks to shift and to create this angle. In the notes, it says the rock has been bent or inclined due to pressure within the crust or within our igneous intrusions. That pressure, grade 12s, could either be the result of two plates moving towards each other, creating folding or faulting, and this is where our rock structures tend to be lifted up and form at an angle. All right, the second note on our board in front of us, it says that the inclined rock consists of sedimentary and metamorphic rock. You would have looked at these specific types of rock in grade 10. Just a quick reminder though that sedimentary rocks are formed where layers of different particles are laid down over time and obviously contain things like fossils, so sedimentary rocks are quite valuable and have good use. Metamorphic rocks form when either a sedimentary or an igneous rock undergoes high temperatures or high pressures, and it changes the chemical formula of that particular rock. Our third point says when homoclinal ridges develop, they always have a dip and a scarp slope on either side. These two words are very important. The dip slope, grade 12, refers to a gentle slope. Okay? And while we're speaking about gentle versus steep, just a reminder that this structural landform work is quite easily tested within the map components as well, because you can see different slopes on your map according to the contour lines. So a dip slope refers to any slope that is gentle, which would imply then, grade 12s, that the contour lines are far apart, and our scarp slope refers to a steep slope. Okay, with our inclined strata, grade 12s, we have three different types of specific inclined strata that you need to learn about, and they all have different names based on the dip slope within that structure. So the gradient of the angle of inclination determines the type of landform. Our first type, number one, that we're going to look at is what's referred to as a cuesta. What's important about a cuesta is that its dip slope is inclined between 10 and 25 degrees. That means that the angle of its dip slope is actually quite gentle and it's not very steep at all. Our second type of inclined strata is what's referred to as a homoclinal ridge. A homoclinal ridge has an inclined dip slope of between 25 to 45 degrees, making it different to the cuesta. Our last type of inclined strata is what's referred to as a hogsback, and its dip slope is inclined at an angle that is greater than 45 degrees. Now, please remember, in terms of studying for tests and exams, that these three different types of inclined strata are very important to remember, and often grade 12s you are asked to give a reason for your answer. If you are to give a reason for your answer, the reason that they are looking for is the actual degrees at which the dip slope is inclined. So if the question says, is this a cuesta? You need to say, yes, it is a cuesta, because the dip slope has an angle between 10 to 25 degrees. That is vitally important that you write that down as part of your answer. Okay, now underneath those three types, it says erosion takes place much faster along the steeper scarp slope and towards the dip slope, because the scarp slope is steeper and some of the softer rock is exposed along the scarp slope. We're going to look at pictures now where that paragraph will be explained much better. So if we move on to the diagrams, you will see that we have got the three main types of inclined strata. We've got a cuesta at the top over here, we've got a homoclinal ridge, and obviously we have a hogsback. Said and mentioned it before, inclined strata is made up of alternating layers of hard and soft rock. From the diagrams here, we can see that this area over here, let's just highlight it with another color. Okay, this particular area over here in terms of all the slopes is what's referred to as the hard rock layer. You will notice then that on the diagram it speaks about resistant quartzite. That resistant quartzite is found in all three types of the inclined strata, and quartzite is an exceptionally hard sedimentary rock that does not erode very easily. On the other hand, you will notice that underlying that hard rock layer, we have what's referred to as soft shale rock. Shale is also a type of sedimentary rock. It is obviously just far more easily erodible as opposed to the quartzite. Previously in the slide above, it mentioned the fact in the last paragraph that erosion takes place faster along the steeper scarp slope towards the dip slope. What that means is if we look at the actual diagrams, that the erosion grade 12s is going to be taking place whereby this landscape is going to be cut back over time. So when they mention that erosion takes place from the steep slope towards the dip slope, that is what we are showing you in the second diagram. Secondly, because the scarp slope is steeper, some of the softer rock is exposed along that scarp slope. And if you can see over here, all of this soft rock is exposed and therefore becomes very easily eroded back over time. And that is what they meant by that complicated paragraph. So please take a look. Notice, I'm going to use the pen to show you, that the angle between the three different types is changing consistently. That means, grade 12s, that those angles are exceptionally important when trying to work out, do I have a cuesta, do I have a homoclinal ridge, or am I looking specifically at a hogsback? I've mentioned before that this work can be tested quite a bit in terms of your map work section, and the reason for that is obviously because of the angle of all these different dip slopes, it's going to influence the spaces between your contour lines on your map. So for example, the dip slope of a cuesta, the contour lines are going to be very, very far apart, as opposed to a hogsback where even though it's a gentle slope, it's still not as gentle as the dip slope of a cuesta, which would then make the contour lines be further together rather than further apart. Okay, right, our last part of our inclined strata that we need to look at is we get what's referred to as basins and domes developing according to the alternating layers of hard and soft rock. So if we look at the computer, it says where the layers have been bent in concentric circles like the next two sketches, homoclinal ridges will form as the layers become eroded. Now what's quite nice about these two diagrams, if we can, okay, we'll focus on the first one. You will notice that these layers have been bent in a dome shape. Okay, so another way of looking at this is to refer to it as a dome. Now, the dome is quite important because what the examiners like to do is they tend to relate the different types of drainage patterns to these inclined strata. And the drainage pattern that is commonly found on a dome, which you studied under drainage patterns, would be the radial drainage pattern. So please remember that you have to relate your fluvial geomorphology to your structural geomorphology. Right, now if you are given a diagram, they'll often say to you, does this diagram represent a dome or a basin, and give a reason for your answer. And that reason is actually quite a simple one. If we look at the diagram over here, you will notice that these steep slopes facing inwards and are referred to as your scarp slopes, and over here, let's just get another color. Okay, let's try again. Okay, these slopes going down over here are far more gentle, and once again they refer to our dip slopes. How do we then identify a dome? It's very simple. You will say your scarp slopes face inwards and my dip slopes face outwards. That would be your reason as to why this would be a dome-shaped feature. So my scarp slopes face inwards, okay, and my dip slopes face outwards. That is the answer that you need to give. Now if we look at the opposite of a dome, which then becomes known as a basin, obviously my dip and my scarp slopes are going to change a bit, which we can see on the diagram. If we look over here, we will notice that that is now the steepest part, and that's why it's referred to as the scarp slope, and these gentle parts over here are referred to as the dip slope. So in terms of looking at a basin, and if you are asked to give a reason for your answer, basically in the basin your dip slopes now face inwards and my scarp slopes face outwards. It's very important that you remember those two specific definitions of a dome and a basin shape. All right, okay, now if we look, we are going to look as the third type of structural landforms. We're looking at landforms that are associated with igneous intrusions. When you see the word igneous intrusions, all that it implies is that magma has come from the mantle, which is the second layer in the structure of the earth, and it has found cracks or joints within the earth's crust in order for the magma to seep through into the mantle, where it solidifies and becomes known as an igneous intrusion. So if we look at the lovely diagram, it says igneous rocks cool down in the crustal layers or earth. Now, very importantly, we can see over here that this has been intruded from the mantle. So the mantle is found even further below this structure. This structure is predominantly looking at the Earth's crust. You can see how the magma comes up from the bottom layers and goes to different parts of the Earth's crust where it finds easy places to go. Quite a bit of the magma will come up through a volcanic pipe. Okay, and once that magma reaches the Earth's surface, please remember it is referred to as lava. Any sort of magma is only found below the Earth's surface. Okay, now the different types of landforms. You have to know, grade 12s, what the different types of landforms are, and you need to be able to identify them on a diagram. So the first and the largest type of igneous intrusions is what we refer to as a batholith. Okay, a batholith, just like it says here in the notes, is an exceptionally large mass of igneous rock that has solidified deep under the surface, and it's predominantly in a dome shape. So the batholith is the largest type of igneous intrusion. A sill, okay, is a layer of igneous rock that has solidified parallel and horizontal with the sedimentary rock that it has intruded into. Please remember that intrusions are of an igneous nature, but they intrude into sedimentary rock. A dike is an igneous rock that has solidified in a fissure. A fissure is like a crack or a joint in the Earth's surface. And very importantly, how does a dike differ from a sill? Is that a dike cuts vertically through the existing rock layers. So your sills are found horizontal to the rock layers, and your dikes cut through vertically at different angles to the sedimentary rock layers. What they can ask, particularly in this section, is give us a difference between a sill and a dike. And like I've just mentioned here, you would obviously then mention the fact that one forms horizontally to the sedimentary rock layers and the other one forms vertically through the rock structures. Our next difference that we need to look at is what's referred to as a lopolith. Okay, a lopolith is a saucer shape. So if you can think of a teacup goes on a saucer. Okay, and that's the exact same shape as what our lopolith would be. It's an igneous intrusion. It once again forms deep under the surface and bends the layer below it downwards. Okay, so these horizontal rocks below the lopolith would be bent by that intrusion. The opposite of a lopolith is what we call a laccolith. And I like to teach my grade 12s that the laccolith has got two C's in it. And if you turn those two C's upside down, you would get the shape of that laccolith. It speaks about it being a mushroom shape. So if you prefer food, maybe that's how you'd like to remember it. And it's also an igneous intrusion which forms near to the Earth's surface. So it forms a bit further up as opposed to a lopolith, and it'll bend the sedimentary layers upwards. So if there's sedimentary rock layers here, those lopoliths would bend them upwards towards the Earth's surface. I've mentioned a pipe before. A pipe is literally a vertical joint or crack within the sedimentary layers, and it is generally linked to a volcanic intrusion. It says cylindrical intrusions through which magma is pushed to the Earth's surface. So if we just go back a page now and once again look at our fantastic diagram, it's important we can point out a few of the features that we have just looked at. So for example, we've spoken about a batholith, and you will notice, grade 12s, that this batholith is a massive igneous intrusion. It's bigger than anything else found on this diagram. Okay, we spoke about a sill. You can see, grade 12s, that that sill is formed horizontal to these sedimentary layers. We've mentioned a dike. Okay, that dike has cut through vertically within the sedimentary layers. We've also spoken this would be a pipe. Okay, it's not labeled as such, but that's where our volcanic pipe would be. Unfortunately, on this diagram, there aren't examples of a laccolith and a lopolith, but as I've mentioned to you, a lopolith is like a saucer, and a laccolith would be a dome-shaped feature. Right. The other types of landforms that you need to study associated with igneous intrusions, we will now be looking at that. It says igneous intrusions form when magma solidifies amongst sedimentary and metamorphic rocks. The examples are what we've already looked at: batholiths, sills, dikes, laccoliths, lopoliths, and pipes. Exfoliation. Now, exfoliation, if you can think of it in terms of something that's real to you, we exfoliate our skin, which means if you take a sponge, you exfoliate your skin and it peels away your dry skin layers. Exfoliation of a rock or a structural landform is identical. It literally refers to bits and pieces of the rock breaking off over time that are no longer needed for use. So exfoliation domes form when large pieces of granite is exposed to the surface and rounded by the exfoliation due to temperature changes. How exfoliation works in terms of our geomorphology is during the day when it is hot, the rocks expand, and at night when the temperatures drop, because this is predominantly once again in a very hot, dry climate, those temperatures cause the rocks to contract. So every single day you have expansion during the day because it's hot, contraction at night because it's cold, and those rock layers become weak and eventually start to peel off in layers. Okay, then it says tors. Tors is one of the most important types of igneous intrusions that you need to learn. It's the one that's most commonly tested in the matric papers. It says they form when the granite dome, that is important, okay? Tors will always form from a dome-shaped feature. That dome is formed by magma intruding into the horizontal sedimentary layers and solidifying below the Earth's surface. It says it's very important, is jointed under the surface. This word jointed. The rocks need to have joints and cracks within them, because for tors to develop, the chemical weathering seeps down below the Earth's surface into those cracks and joints and starts to enlarge them because the chemicals react with the rock structure. When the granite eventually becomes exposed to the surface, all the weathered material is eroded away and a stack of boulders is left on the surface, and those are referred to as our core stones. So when they refer to these boulders, please note the correct geographical term is what's referred to as the core stones. Okay, here is a diagram now to explain the formation of our tors and their development. So if we look over here, there's quite a lot going on in this diagram, so we're going to explain it as best we can. Alright, here you have a dome-shaped feature that has formed below the Earth's surface. So that is referred to as an igneous dome. Okay, you can see there's the Earth's crust layer, and this dome has formed below that surface. You will also notice on the diagram that it is well jointed. So it has all these spaces here between the rocks, along which chemical weathering can take place. So we have water seeping through the Earth's surface towards these joints, and obviously the chemical weathering process occurs. Okay, this diagram over here, it says joints form underground and allow chemical weathering to take place. Soil above the dome is eroded away, and chemical weathering has enlarged the joints and the cracks, because obviously it's seeped through there and it has caused the erosion of various types of material. So you will notice that these core stones are starting to develop ever so slowly. And the second diagram over here, you can see that further development of those core stones has taken place. It says stacked rocks stand out above the landscape. What you will notice is between these two processes, the underlying rock structures have been exposed through weathering, and due to that weathering, they have become visible on the Earth's surface. One of the best examples of tors in South Africa is actually found just up the road here from where we're shooting, in an area called Lone Hill, and all you will see in that specific area are these massive boulders of rock lying on top of a rocky igneous outcrop. Okay, that brings us to the end of our actual theory and lesson session. Like I've said to you before, it's very important, grade 12s, that because the structural landscape section is not very difficult, there's lots of learning work that you can do to score quite a few marks. First of all, just a reminder, we looked at the horizontal sedimentary layers, and under those layers I said you need to remember a plateau, a mesa, a butte, a pointed butte, and a conical hill. Under our inclined strata, I mentioned that it was very important to learn the difference between a cuesta, a homoclinal ridge, and a hogsback. And lastly, under igneous intrusions, we looked at things like our batholiths, our laccoliths, our lopoliths, sills, and dikes. And more importantly, under our igneous intrusion, we have studied granite intrusions and tors. Very, very important. It's simple information that you can learn over time. So if you join us after the break, we will be looking at some questions on these structural landforms that we have just learnt about, and how to answer the questions in a final exam. We'll see you after the break. Welcome back after the break, and we are once again looking at part 3 of geomorphology, where we have looked at our structural landforms, and we've already done all the theory parts, so it is now time to look at specific questions that are related to the structural landforms topic. Our first question, it says, figure A below shows a landform typically found in South Africa. Figure B shows the process of mass movement that will take place on the slopes of the illustrated landform. Now, we have not done a recap on mass movement, but that was covered in part 2 of the geomorphology sessions. But just a reminder that mass movement is material that moves down a slope under the force of gravity. So our first question related to the above diagrams says to identify the landform or feature that is illustrated in figure A. So if we look at figure A, a couple of ideas here to get what we're looking at. I reminded you that we only looked at 3 different types of structural landscapes. We've looked at horizontal landscapes, inclined rock strata, and we've looked at massive igneous intrusions. Now, as we look at the diagram here, the clue that gives it away as to what it is, it has a label of resistant rock. The only type of structural landform that has resistant, particularly rock, and it's sitting at a bit of an angle, would be one of our inclined rock stratas. And if you think back to how to determine which specific type, I will remind you that it is the angle of the dip slope that becomes necessary in this case. And if I look at the diagram in front of me, this area over here is a very steep area, so that would be referred to as my scarp slope, and these areas going back down the mountain here would be referred to as my dip slope. And in this particular case, the angle of the dip slope is not very steep at all, which would make the landform illustrated above a cuesta. Just a reminder, a cuesta, the dip slope is found anywhere between 10 to 25 degrees, and that's your reasoning behind that. Our next question, based on the exact same diagrams, explain with reference to the underlying rock structure how the landform identified above developed. So they want to know actually how did a cuesta or inclined strata develop. Now, it's for 6 marks, but if we look at the actual mark allocation, they are only specifically looking for 3 different points. The very first point that you should be giving to answer this question is that our sedimentary rock layers are tilted. You can see that that rock structure is lying at an angle. You can also see it spoke about the underlying rock structure. We know that inclined rocks have developed when we have alternating layers of hard and soft rock. So you could use that as a second point, saying that the rock structures vary in their resistance to erosion. Okay. And you could speak also about the fact that our soft rocks are eroded away to form our valleys. Your steeper slopes protrude out to form the ridges of that landscape. There are a variety of different reasons, and definitely can put together 3 in terms of this answer. If we look at our next question, in the intro to the question, it mentioned mass movement, and I said to you that's the movement of material down a slope as a result of gravity, and they specifically want to know the type of mass movement that would be found in this specific diagram over here. Because the gradient of my dip slope is not very steep, the type of mass movement that would occur on that specific slope is soil creep. Now, soil creep, just a reminder, is the most gentle, slow-moving type of mass movement. It is not a very fast or quick process that occurs. Secondly, Provide evidence from figure B that mass movement is taking place. And this is quite a nice question, because if we actually look at that specific diagram, we can see a lot of the answers that they want are written in this diagram. For example, tilted telephone poles would be one of the answers they need for that question. Why is the telephone pole tilted? Because mass movement has taken place, causing an imbalance in the sturdiness of the rocks below it. We've got trees turned down slope. That could be another possible answer there. We have terrace sets, okay? Terrace sets, grade 12s, don't get worried. It's just a fancy word for them speaking about a terrace. What is a terrace? If we draw a little imaginary diagram over there, terrace is when almost steps are created in that soil profile. We've also got gashes in our road. You will see there are 4 possible answers, and for that specific question, they're only looking for one specific answer, which comes exactly from the diagram. Okay, our next part of the question then says, on which slope specifically, either the dip slope or the scarp slope, is mass movement more likely to take place? We've explained this earlier, that our dip slope is our gentle slope and our scarp slope is our steep slope. So it becomes very obvious there in grade 12 that our mass movement will take place on the much steeper slope. Our next question. Explain your answer. Okay, so they want to know, why does the mass movement happen on the much steeper slope or on the scarp slope? So as a reason behind this, you could say the scarp slope of the two is the most steep of the two, therefore mass movement happens quicker on that slope. Also, gravity is going to influence the steeper slope more, because it's sitting at a much steeper angle, allowing the material to move faster. And you could also mention the fact that material moves more easily down a steep slope, once again relating to the gravity. Okay, our 5th question. Why do you think people should be made aware of the consequences of mass movement before building on our slopes? Go back to your mark allocation. They would like to know 2 points as to why it's important for people to be aware that mass movement can occur on the slopes. Very simple, okay? Our buildings can be destroyed if the ground below us begins to move. Our roads can be damaged if they don't have the proper foundations, especially those roads that are built in much steeper parts of our country. To repair our buildings and our roads can be exceptionally costly, and people must take proper precautions before building. Good foundations, good engineering, that kind of thing needs to go into the building process. All right, our last question. Name one way in which slopes can be stabilized or reinforced to reduce mass movement. Now, for this specific question, they have only asked for one example, but I have seen quite often that the examiners tend to like to turn this specific question into a paragraph question. So I'm going to give you more than one particular way in which we can stabilize our slopes, and therefore you can write them down and learn them in case you need to answer a paragraph question. First and foremost, to stabilize any slope, it is important that we plant vegetation on that slope. Vegetation has got roots. Those roots bind the soil, and that stabilizes that piece of land. So stabilizing the land, plant lots of vegetation. Secondly, grade 12s, we can put safety nets to catch any falling materials. In the Western Cape by Chapman's Peak, they have carved the road through the very rocky mountainside. They have safety nets along those rocky outcrops to prevent rock falls from that structure from affecting the drivers on the road or the cyclists in particular. We can also lay down mesh wire. Okay, so mesh wire has got little parts through which vegetation and that can still grow, and that mesh wire also tends to bind the soil. We can create rock embankments to prevent the movement down the slope. So we could literally terrace our own slopes to slow down that movement. We could build tunnels, okay, so that the cars and the cyclists go below the earth or below the rock structure. And we need to do proper environmental impacts assessments when we are looking to build in a particular area. Okay. Question 2, it says, the figure below illustrates the development of a structural landform associated with massive igneous rock. So they are specifically telling you which type of structural landforms they want us to focus on in this question. Right, if we look at the two diagrams, there they are. And our first question says, identify the landforms G and H respectively. Now, just by looking at those diagrams, that's a nice dome-shaped feature. Therefore, feature G is actually a dome. Okay. If we go to figure H, we will notice that we've got nice jointed igneous granite rock over here. That is going to definitely be what's referred to as a tor. And if you remember or recall earlier, I mentioned the fact that a tor is the most important type of massive igneous intrusions. Our second question, based on the same diagrams, name the original underground igneous landform from which landform G and H originated. They're looking for the greatest or the largest type of massive igneous intrusion, and we've mentioned this before. Our most large igneous intrusion is what's referred to as the batholith. Alternatively, they could have also formed from a laccolith below the Earth's surface. If you remember, the laccolith was our mushroom dome-shaped feature. Our third question, briefly explain how H develops. So it's very important, you can see, that you get the right landform in the first couple of questions, because otherwise, if you don't know what specific landform you're looking at, to explain how that landform developed is going to be a lot more difficult. Please note, it's for 6 marks. They want 3 points as to how our tor developed. Okay, for a tor developed, we need well-jointed igneous rock. That would be the first point in your answer, that we need granite rock that is exceptionally well jointed. Okay, our second point would be the fact that we need chemical weathering to occur along the well jointed rock. So our first point was that our rock needs to be well jointed. Our second point is that we need chemical weathering to occur. And our last point, which you can write down, is that we have to have the weathering and erosion of the surface material exposing the underlying rock structure. So those are your 3 specific points that you need to write down for the formation of a tor. Okay, moving on. 2.4. Briefly explain how landform G develops. So like I said to you before, it's very important that you get landform G and H correct, otherwise your explanations are going to be very difficult. Okay, once again, you will see our question is looking for 3 separate points. So for landform G, let's just go up to it so that we can look at it while we're explaining. A batholith, because that's the original igneous intrusion that occurred below the Earth's surface, becomes exposed to the surface due to the erosion of the softer soil around it. So you've got a batholith that formed below the Earth's surface, and over time, weathering and erosion has exposed that batholith to the Earth's surface. What happens then is our dome gets rounded through the process of exfoliation, which we explained earlier in the session, and it starts to even out the uneven parts on that dome. And lastly, for your third point, the dome stands out as a solid mass of igneous rock. Okay, 2.5. It says, what drainage pattern will develop on landform G? We mentioned earlier that landform G is our dome-shaped feature, and I said to you when we were explaining the theory that it's very important to remember your fluvial geomorphology when you look at your structural landforms. The type of drainage that will develop is what's referred to as radial drainage pattern. Okay, and it's literally, if that's your dome-shaped feature and it rains above it, the rain is going to run down the various sides of that specific feature, creating that radial flow. Our last question for question 2, explain why the drainage pattern you have identified will develop at G. I've shown you the diagram in the previous question. Basically, if we have to explain it, you can say that the water drains from the highest point in the middle of the dome to all the lower points in all different directions. If we were to draw an aerial view of how this would happen, you would notice that the water drains away in all different directions, creating what's referred to as my radial drainage pattern. Okay, so please note that you have to be able to mix up your fluvial geomorphology with your structural landforms. All right, question 3. Okay, figure 3 below illustrates a structural landscape typically found in the Karoo. They're giving you a hint there. If they mention the Karoo, they're specifically looking at our horizontal landscapes. Okay, question 3.1. Identify landforms P and Q respectively. Now, we've looked at the different types of landforms. P is obviously a much larger size as opposed to Q. Therefore, P would most likely be what's referred to as a mesa, and Q would therefore be a butte. I just want to point out while we have the diagram on the screen that the information given below is also of very, or you should take particular note of it. It speaks about dolerite. Dolerite, you will notice, is the hard cap layer of our sedimentary or horizontal rock strata. Below that, we have sandstone, which is a relatively more resistant rock to erosion, and underneath it we have a whole lot of shale. What happens here, grade 12s, is that they decrease in their resistance to erosion. So dolerite would be your most resistant to erosion, and shale would be your least resistant to erosion. 3.2, same diagram. What evidence in the figure 3 suggests that landforms P and Q developed from the same landform that existed earlier? Okay, they're looking for 2 specific answers over here, and basically what's important about a horizontal landscape is that a horizontal landscape retains its vertical height. The landforms are eroded parallel, but they do not get altered vertically. So that's one reason that they develop from the same piece of original landscape. They both have the same hard cap layer. Okay, they both have the same rock layers, which would indicate that they've developed from the same landform, and there's more than enough answers there for you. Okay, question 3.3. Which rock type is the most resistant to erosion? I've pointed that out to you earlier when we looked at the 3 different types, and the hard cap layer of a Karoo landscape is always going to be the most resistant to erosion. So in this case, it is the dolerite that is the most resistant to erosion. All right. 3.4. Give one reason for your answer in question 3.3. So they want you now to prove or explain why dolerite is the most resistant rock. Okay. The reason why it's the most resistant rock, and it's the most pertinent reason to these questions, is that the original height of the landscape has been maintained. So the landscape is not eroded vertically, and the original height of the landscape has been maintained over time. You could also say things like it's the hardest rock layer that protects the structures below the area over here. Anything along those lines. 3.5. Briefly describe how landform P will change into landform Q over time. Okay, this is quite an important question, and it's often referred to as scarp retreat, parallel retreat, something like that, but basically it's quite an important question because it's worth 3 marks. You need to write down exactly what the examiner is looking for. Okay, so as mentioned before, the erosion takes place along the sides of the landform. So it's not altered vertically. The softer rock over here becomes eroded over time. Okay, and eventually, because the underlying rock layers here have been eroded away, the hard cap breaks along with those structures. Okay, so points that you should probably write down for this question include things like they get eroded through running water, so a river, back wasting or scarp retreat occurs, parallel retreat of the slopes, eventually the height of the feature is greater than its diameter, and things like that would help you to answer this question. So it says, briefly describe how landform P changes into landform Q. It is important to speak about the erosion taking place parallel, that kind of thing. Okay, moving on to question 4. It says, refer to the figures below showing the development of a landscape associated with horizontal sedimentary rock. The 3 diagrams are not arranged in the correct order of development. Question 4.1. Arrange the 3 diagrams in the correct order of development by writing the letters that appear on the diagrams in the correct order. So we have diagrams A, B, and C. They want us to put them in the correct order. Now, clearly you can see in picture A that there's no hard cap layer left or anything like that. So A is definitely not going to be the first. It's most likely the last picture. Picture C, it shows us a nice mesa that's developed. We can still see the hard rock layer, and we can see the erosion that's taken place on the sides. B, you can still see quite a bit of that landscape. So we have to put these diagrams in the correct order. B is going to be first because we can see the whole landscape is intact, followed by C. And lastly, when the hard cap layer is removed, we will then put diagram A. Okay. The utilization of landscape B by humans is limited. Explain the reasons for this. It's been described to grade 12s as the Karoo landscape. The Karoo landscape is typically a desert area. The geographical term for a desert, they speak about arid conditions. If we speak about arid conditions, it implies hot, very little vegetation. Okay, so explain the reason why this landscape is not going to be able to be used. It is arid. The temperatures are high. The vegetation is lacking. You could also say things like the soil in that area is going to be exceptionally infertile. That's possibly due to the lack of vegetation. The rivers flow in a deep-sided valley, so you can't even get access to those rivers because they're too far below the surface. You can't have any agriculture or settlement in this area, okay? No one wants to live there. And possibly the only use for these particular landscapes is what's referred to as adventure tourism. You could have a bungee swing between the canyon parts, things like that. Okay, question 4.3. Which one of the diagrams illustrates a typical Karoo landscape? And like I've said to you before, it's going to be letter C. This is most likely a mesa or a plateau or something of that nature. 4.4, identify the landform in the diagram mentioned in question 4.3 that is typically found in the Karoo landscape. We've jumped the gun there, I've written it on the slide before that, but this would be an example of a mesa. Okay, our last question for 4.5, give a reason why cuestas will not develop in the landscape visible in the figure above. A cuesta is an example of inclined strata. Okay? You cannot have inclined strata forming in the same area as where we have horizontal strata. So a cuesta will not form in this area because a cuesta is in a form of inclined strata, and the diagrams given above are examples of horizontally layered strata. So that's your answer for 4.5. Okay. Question 5 says, refer to figure A and B below showing a landscape typical of inclined sedimentary layers. Figure B illustrates a drainage pattern that will most likely develop in the landscape shown in figure A. Once again, they are relating fluvial geomorphology to structural landscapes. Okay, the first question asks us to name the landforms labeled R in figure A. Now, it is quite difficult over here that they've mentioned that it's inclined strata. Once again, we have to look at the angle of this dip slope running back in that direction. Either way here, I would give an answer of it either being a cuesta or a homoclinal ridge, because you can't get an accurate idea in terms of the steepness of those dip slopes. So basically what I suggest is that you write down a homoclinal ridge or possibly a cuesta. Question 5.2. Briefly describe the development of the landscape illustrated above. Once again, it needs 3 points, okay, so quite a bit of marks. We're going to say the answers slowly so that it'll give you time to write them down. How this landscape has developed is as follows. Sedimentary rock layers have been tilted. Okay, that would be your first point. Sedimentary rock layers have been tilted. Okay, your second point would speak about our softer layers erode faster, creating our valleys. So our softer layers erode faster to create our valleys. And our hard rock layers erode slower to produce the ridges. So once again, it's mentioning there the alternating layers of hard and soft rock. You've got some sort of tectonic activity that has caused those landscapes to form at an angle, and as a result, these layers protrude above the surface. Okay, 5.3. Name the drainage pattern illustrated in figure B that will develop in the landscape shown above. You should automatically relate alternating layers of hard and soft rock to a trellis-shaped drainage pattern that is shown here in the diagram. So the answer for 5.3 is trellis, and if you go back to your fluvial section, when you are learning your drainage patterns, we've mentioned before that it's critical that you learn the underlying rock structures as well. Question 5.4. Explain why the drainage pattern mentioned in question 5.3 will develop in this landscape. And I've mentioned it time and time again. It's alternating layers of hard and soft rock. That is critical for a trellis pattern to develop. They're looking for more answers than that, so that should be your first answer, alternating layers of hard and soft rock. You should also mention the fact that your short tributaries will flow down the ridges to meet the main streams that will flow in the valleys. And you can say that the tributaries will join the main stream at right angles. If you look at the diagram over here, where these streams are entering, they all form 90-degree angles. Question 6. Rocks have different types of strata, which gives rise to unique landforms. Use the figure below to observe some of these landforms and answer the questions that follow. Identify the features or landforms labeled E and F. Now, this diagram is a little bit more confusing than the previous diagrams that we've seen. The reason why is over here, this rock structure is sitting at an angle, which would make it a form of inclined strata. And this strata over here is lying horizontally. So on the same diagram, they are showing you horizontal rock strata, and they are showing you inclined rock strata. Now, please don't make the mistake. They have specifically in the question referred to the features. If you are looking for a feature, you are not being asked for the type of structural landforms. So I've mentioned here that E is a type of inclined strata and F is a type of horizontal strata. But what the question specifically looks at is the actual feature. So once again, we're not given the angle of this dip slope, therefore you could mention either a cuesta or a homoclinal ridge, because if it was a hogsback, it would need to be a lot steeper than that. So for landform E, it is either a cuesta or a hogsback. Landform F, if we take the majority, and once again, it's very difficult to judge the size and the scale of that feature, but more often than not, they are looking for a mesa. A mesa is an example of horizontal rock strata, and a cuesta or homoclinal ridge is an example of inclined strata. Okay, question 6.2. Give one difference between feature E and F. Now this is very, very easy, okay? I've pointed it out to you before. E is a feature of inclined strata, so rocks that are sitting at an angle. F is a feature of horizontal strata, okay? Other ideas here that you may use is E is tilted more in relation to the Earth's surface. Obviously your horizontal rock strata doesn't get tilted at all. E has two steep slopes, okay? F has similar slopes on either side of it. So most importantly, I would believe for the difference between the two is that E is a type of inclined strata and F is simply a type of horizontal strata. Okay, question 6.3. Of what value is this landscape to man? Give two reasons. Now, I think because there's two different types of strata here, we've mentioned that E is inclined and F is horizontal. Basically, you know, we try and look for one sort of advantage on each type. For example, if we are located at the top of this horizontal structure over here, that becomes very important in terms of a country's defensibility. So in terms of looking at the defense of a settlement, that sort of high ground would offer that as an advantage. If we look at our homoclinal ridges over here, the softer layers on the dip slopes form very fertile soil, good for agriculture. They got a nice gentle gradient. Our steep slopes could be used for forestry. So there's quite a few ideas here that makes these slopes quite useful. Also, in terms of the steeper slopes, we could use them for hiking, so they make good tourism sites. Building houses in the gentle dip slope would be valuable as well. Nice advantage there. All right, question 7, it says, refer to the figure below showing a landscape found in South Africa. 4 options, so this means it's multiple choice, are provided as possible answers to the following questions. Choose the answer and write only the letter next to the question number. This diagram is very similar to one we've had before in terms of the horizontal landscape. However, they've added an extra dynamic to it by labeling our slope elements along the same diagram. Remember, your slope elements were previously done in session 2, and let's just quickly recap on what those would be. So W is pointing at the top of our slope here, and that would be what's referred to as our crest slope. Hopefully this is ringing some bells and reminding you that all of these sections can be interlinked. X we refer to as our scarp slope, okay, Y as our talus, and Z as our pediment slope. Those are our 4 different slope elements. So we've got the crest, scarp, talus, and pediment. Also, very importantly, I want to point out at that point over here where the gradient changes between the talus and the pediment slopes, that area is referred to as a nick point. Okay, so now that we've reminded you about those important concepts, let's look at our multiple choice questions. The landscape illustrated in the figure above is associated with what kind of rock? Now, under structural landforms, we've only done 3 types of rocks, so there's already too many options here because there's 4 answers. It is definitely not massive igneous rocks. Massive igneous rocks are things like our tors, our domes, our batholiths, and this diagram is showing none of those such things. Horizontal sedimentary rocks, most definitely, okay? You can see by the layout of these rock layers, they are parallel to the Earth's surface and occur in horizontal layers. The 2 other options below, tilted igneous, tilted sedimentary, no, because nothing on this diagram is sitting at an angle to the Earth's surface. So 7.1, that picture is definitely an example of horizontal sedimentary rock. 7.2, landform P is a, so let's go back. There's landform P. We've looked at this diagram in previous questions. It's a type of horizontal rock. So let's go to our answers, and the very first one is exactly what we are looking for. A cuesta is a type of inclined strata. All right, our butte would be landform Q from the diagram, okay, because a mesa gets eroded to form a butte, and a tor is an example of massive igneous rock. So the answer for 7.2 is most definitely a mesa. Okay, 7.3. Slope element Z. You see, so if we look at the diagrams before we look at the questions, some of our answers might already be obvious to us. So if we go and look at the diagram now, slope element Z is over there. We've already labeled it as the pediment slope. So if we go and look, our answer is D. Okay? Right. You will notice they've got the answer cliff here, A cliff slope could be another name for a scarp slope. So most of the slopes actually have one or two names that could be used in their places. All right, 7.4. The landscape above is typical of what kind of regions in South Africa? It's found in the Karoo. It's a Karoo landscape. The Karoo, grade 12s, is a hot, dry, arid area. So if we look at the options, humid and hot. Humid implies a lot of moisture in the air, a lot of rainfall, so unfortunately anything that says the word humid is not right. C also says humid and cold. That is not correct. We've mentioned it has to be hot, so we can take out D because D says dry and cold, and therefore the answer is definitely going to be a dry, hot area. That name, once again, it refers to an arid area. Okay, grade 12s, moving on to our last of question 7. We look at 7.5, and it says the landscape is typical in which province of South Africa? We have spoken so many times that the only province in South Africa that is hot enough, very dry, and typical of a Karoo landscape is the Northern Cape. Mpumalanga, KwaZulu-Natal, they get far too much rainfall, so those don't even come into it. And in Gauteng, we definitely don't have lots of structural landforms around us of great importance. Okay, moving on to question 8.1b, it says, state one significance of ridge A to humans. We have had a similar question from previous questions that we've already looked at. So just a reminder, some of the options that you can give in this question would be things like it's a good, the slope was used in times of war to protect the settlements from an attack. We could also farm in the soft, fertile plains between the ridges, so our gentle slopes. And thirdly, you could also mention that water traps which act as artesian basins between those ridges and therefore also makes it very good for farming. Okay, the next question, which is 8.1c, briefly explain how ridge A formed. So they want to know, how did the strata get inclined and sit at the specific angle to produce the diagram seen? Very, very importantly, you have to mention that it forms in areas where there has been faulting or folding. Okay. You also need to mention that it will form in areas that have alternating layers of hard and soft rock, so something like a quartzite and a shale. And you would then further go on to say that the softer shale rock will get eroded to form our valleys, and our harder rock protrudes outwards as a ridge sort of area. Okay, so those are the things that they look for when they're asking you to explain the development of our ridges. Moving on to question 8.2, it says identify slopes B and C respectively. Now, they don't specifically mention, but this you can see has got a gentle gradient. Therefore, grade 12s, it gets referred to as the dip slope. Just a reminder that our dip slope is gentle. Okay, slope number C is our scarp slope, and I always remind my grade 12 learners that the S's go together, so scarp implies that it is the steeper of the two slopes. So we've got B, which is our gentle dip slope, and C, which is our steep scarp slope. Okay, 8.3. Mesas will not develop in this landscape, and give a reason why this is so. I've spoken to you numerous occasions now. A mesa is a form of horizontal strata. Okay, and the diagram that we're looking at above is an example of inclined strata. Therefore, a mesa cannot develop in an inclined strata area. Okay, that brings us now to the end of our geomorphology questions, particularly based on our structural landforms. And this is the final session of geomorphology. We have done all the work covered in geomorphology up to this point. So please note that you should watch all 3 sessions to get your geomorphology knowledge up to scratch. And hopefully this will help you with your final examinations at the end of the year.